This tape is on exponents, Chapter A. Repeated multiplication of a single number or letter can best be represented in its simplest form using exponents. That statement summarizes the purpose for studying exponents. For example, 7 times 7 times 7 times 7 times 7 again is a mathematical expression which shows that 7 is multiplied by itself 5 times in succession. I have used the time sign to indicate multiplication here, but later on I will show you other ways where multiplication is indicated as well by using other signs. This, of course, can be written and shown equal to 16,807. But there is another interesting and simple way to write that expression, which is the reason for this lecture. And it is this: is also equal to 7 raised to the 5th. This expression is called an exponential expression. Take careful note of two very important observations. The number 7 is written in normal size, whereas the number 5 is written very small and is raised. In general terminology, the 5 is called a superscript. Because superscripts have a special application in this lecture and in mathematics generally, superscripts such as 5 will always be properly referred to as exponents. On the other hand, at times, we may have to expand exponential expressions such as 7 to the 5th, showing all of its parts. That is, beginning with 7 to the 5th, we can interpret that as meaning. And I'm going to use another way now to show multiplication. 7.7.7 5 times in succession. And here is another way to indicate multiplication as well. 7 to the 5th can also be shown as equaling brackets 7, and so on until. There is yet another way to show continuous multiplication that is commonly used, and here is an example of that. X to the 5th can be written as x times x times x times x times x without any multiplication sign or dot or brackets. When a series of variables is listed without signs between them, multiplication is always intended. The general expression used to represent exponentiation is to the mth. Here, x can represent any real number. And to show that x is any real number, we usually show that in the following way. X is an element of R. Capital R represents the real number system. And M is an element of N. Capital N here represents the natural number system. Here is more terminology. X to the mth is called a power. What I have enclosed in this box then is referred to as a power. M, as I've already explained, is the exponent, and x is called the base of the power. Here are some worked examples. Is equal to 3 times 3 multiplied by itself 5 times. As a number, this is equal to 243. Another example, 5 squared x cubed is equal to 5 times 5 followed by x times x times x, or 25x cubed. Here are more examples worked out. Expand and simplify the following. 3m raised to the exponent 4 can be interpreted to mean 3m multiplied by 3m and so on 4 times. We can simplify this to show that 3 is multiplied within the expanded list 4 times as follows, and then 4 m's. This then simplifies to 81 m to the 4th. Another example, negative 2p quantity squared is equal to negative 2p followed by negative 2p. And that is the same as negative 2 times negative 2 multiplied by p times p. Negative 2 times negative 2 is positive 4, and we end up with positive 4p squared as an exponential expression. The next topic in the study of exponents is the multiplication of powers. If two powers, such as x to the 5th and y to the 3rd, are multiplied, nothing can be done to the expression except to write it in the following way. X to the 5th times y to the 3rd can only be expressed as x to the 5th, y to the 3rd. But on the other hand, if we take two powers such as x to the 5th times x to the 3rd, the expression can be simplified. Observe that x to the 5th is equal to x multiplied by itself 5 times, and that x to the 3rd is equal to x multiplied by itself 3 times. Consequently, if we take x to the 5th and multiply it by x to the 3rd, is equal to 5 x's in a row like that, followed by 3 x's in a row like this, and that the right-hand side is equal to x to the 8th. The preceding example is summarized in the following rule, or law of exponents. Multiplication of powers having the same base. If m and n are elements of the natural number system and x is a member of the real number system, then x to the m times x to the n is equal to x to the m plus n. Memorize this rule. Here are some examples. X to the 5th times x to the 12th is equal to x to the 5 plus 12, which equals x to the 17. Another example, 3x squared x to the 6th is equal to 3x to the 2 plus 6, which is equal to 3x to the 8th. Another example, 2x to the 3rd followed by 7x to the 9th is equal to 14x to the 3 plus 9, which is equal to 12. Another example, negative 4c squared, c cubed multiplied by c. This results in the expression negative 4c raised to the 6th. The next topic in the study of exponents is division of powers. If two powers, such as x to the 5th and y to the 5th, say 3rd, are divided, x to the 5th over y to the 3rd. But two powers such as x to the 5th divided by x to the 3rd is equal to x times x times x times x 5 times, and that x to the 3rd is again x times x times x divided by x to the 3rd, that we have the right-hand expression over written out as a fraction as well. We notice that for each factor in the box, upper part of the fraction, there is a matching factor below, and consequently each of these can be replaced by a 1, and so simply x squared. We can conclude then that x to the 5th divided by x to the 3rd is equal to x to the 5 subtract 3. The example I have just done can be summarized in a general rule referred to as Rule 2. Division of powers of the same base. If m and n are members of the natural numbers, and x is an element of the real number system, then x to the m divided by x to the n is equal to x to the m minus n. Be sure you subtract in that order. Memorize this rule. X to the m divided by x to the n can also be written as a fraction, as I have explained earlier. X to the m divided by x to the n is the same as x to the m upon x to the nth. Here are some examples. Divide x to the 12th and x to the 6th. This is equal to x to the 12th subtract 6, which is equal to x to the 6th. Another example, 3x to the 7th divided by x squared is equal to 3 x to the 7th subtract 2, which finally reduces to x to the 5th. Another example, 7x to the 5th, y to the 4th, divided by 2x squared, y to the 3rd. 7 over 2 will, working with x to the 5th and x to the 2nd, subtracting exponents, the result is x to the 3rd. Similarly, y to the 4th divided by y to the 3rd, subtracting exponents, we end up with y to the 1. We'll extend this line a little. Here's another example. Negative 4a to the 12th divided by 2a to the 7th. We can simplify the coefficients here. Negative 4 divided by 2 is negative 2. And working on the exponents of the powers which are divided, we have a to the 12 subtract 7, and that equals 5. Another example, 15 times 10 to the 12th divided by 5 times 10 to the 7th. 3 followed by 10, simply 5. The next topic in the study of exponents deals with the case where the base is an exponential expression. If you start with an exponential expression, such as x to the 5th, it can be raised by another exponent, such as 3, to form a new composite power. Now, x to the 5th is the base to the exponent 3. This expression is often appropriately referred to as a power of a power. The meaning of this composite expression can be explained by going back to basics. X to the 5th raised to the exponent 3 is equal to x to the 5th multiplied by x to the 5th multiplied by x to the 5th 3 times. X to the 5 plus 5 plus 5. That in turn is simplified to equal x to the 15th. It is simpler to learn a new rule regarding the power of a power expression, and it is as follows. X to the 5th raised to the power 3 is equivalent to x to the 5 times 3. This is equal to x to the 15th. So, for Rule 3, which we refer to as the power rule, if m, n are elements of n, the natural numbers, and x is an element of r, the real numbers, then x to the m raised to the n is equal to x to the m times n. Memorize this rule. For example, x to the 4th raised to the 3rd is equal to x to the 4 times 3, which in turn is equal to x to the 12th. Another example, 3x squared to the 5th is equal to 3 to the 1 times 5, x to the 2 times 5 is equal to 3 to the 5th followed by x to the 10th, or 3 x to the 10th. Another example, negative x cubed raised to the 4th is equal to, the negative 1 is affected by the 4 and consequently can be observed as followed by x to the 3rd multiplied by 4. This is equal to positive x to the 12th. Another example, negative 3a to the 6th raised again to the 7th. This is equal to negative 3 to the 7th followed by a to the 6th times 7, and this is equal to, is negative 2,187 a to the 42nd. Another example, x cubed y squared raised to the 3rd is equal to x to the 3 times 3 followed by y to the 2 times 3. And this eventually is written as x to the 9th, y to the 6th. Another example, x to the 3rd over y squared, all raised to the exponent 3. This is equal to x to the 3 times 3 over y to the 2 times 3, which eventually becomes x to the 9th over y to the 6th when simplified. You now have all the basic rules, sometimes called laws, of exponents to do any problem which requires simplifying exponential expressions. The 3 basic laws were introduced with the exponents restricted to only natural numbers or the counting numbers. But to advance, we must relax this restriction to make a more general and more reaching statement. And it is this: All of the three laws listed earlier will also apply when the exponents are real numbers.